actually, let me just do one of them here. I want to look at this question, and this is number L, or letter L here. And this one, I'm going to use a different equation for this, which is also something that we normally would use in chemistry. But remember, chemistry and physics are often closely linked. It's just that chemistry is more interested in things at the atomic level, so it's more specific about what it's looking at. So what I want here is I have a 0.5 cubic meter cylinder of nitrogen gas. It's a diatomic molecule. It's held at 65 degrees and is contained by a 25 kilogram piston pressing on a circular disc with a diameter of 25 centimeters. The piston is lowered onto the gas using only the acceleration of gravity, and I want to know what is the mass of the gas. So this kind of presents me with a bunch of different ways of looking at this, but the thing I see right away is I see that I have volume. So volume is interesting. I know that this piston pressing on a circular disc must give me some kind of pressure. So if I look at this, I have pressure, I have volume. It wants to know mass, and it is also giving me temperature. Well, this looks an awful lot like PV equals nRT, okay, because I've given everything, and I can get mass from moles. And so I'm just going to use this equation here. Now, this is going to be slightly different than the way I teach this in chemistry, in that I'm not just taking a certain pressure, I'm going to actually have to calculate the pressure. And so to calculate pressure, we have to remember that pressure is equal to force divided by area. And so they've given us all the information we need to calculate that. So let's do that first. I have a 25 kilogram piston pressing on a circular disc with a diameter of 25 centimeters. So the 25 kilogram disc, it says it's only being lowered by the acceleration of gravity. So there's my force right there, right? 25 kilograms times 9.8 meters per second squared gives me my force. And then the area, I can take the area of the circular disc, because I know that I can use pi r squared to get my area of the disc there. So I'm going to use pi. It has to be in meters, so this is going to be 25 divided by 2 to get the radius, divided by 100 to get the meters, and so it's going to be 0.125 meters, and I'm going to square that, and that gives my pressure right there. Okay, and that's so, and it'll be in pascals. That's essentially what pascals gives you. Now I have volume, so we'll take this whole thing. I have a volume of 0.5 cubic meters, and I want to find mass. But first, I'm going to find moles, because if I can find moles, it's pretty simple to find the mass. And so, N is my variable that I'm looking for. And then I'm going to use my handy dandy 8.31. This is my universal gas constant, and so it's 8.31, and it'll be pascals times, times meters cubed. And we're dividing that whole thing by kilograms. We'll say Kelvin times moles. I kind of got this backwards, but that still works. And then I'm going to get temperature. Now remember, in gas laws, you always have to have temperature in Kelvin. So I'm going to do 273 plus 65. And I'm going to solve for N. Okay, it's a little bit of a complicated problem, so let's try this. 25 times 9.8 divided by pi divided by 0.125 squared gives me a pressure of 4,991 pascals. That's not very high, actually. It's a pretty low pressure in that. Times 0.5. I'm going to divide out the 8.31, and then I'm going to divide out the 273 plus 65. And I get this is equal to 0.8885 moles. Okay, and then to get mass, I'm going to multiply by the molar mass of nitrogen gas, which is going to be 28 grams per mole. So that's just multiply that by 28, gives me my number, which is going to be equal to 24.9 grams. Okay. Okay, and so I'm gonna kind of, the last little question I might look at is say, what is the kinetic energy of gas? So the kinetic energy of gas, what you want to use is this equation here, where it's 3/2 times Kb, which is the Boltzmann's constant times temperature. And again, gases we have to have in Kelvin. So to get the kinetic energy of the gas, I'm going to take 3/2, so 1.5. The Boltzmann's constant is 1.38 times 10 to the negative 23. And then our temperature of this gas, 273 plus 65, was 338. Okay, and this will give you an energy in joules. So 1.5 times 1.38 e to the 23 negative times 338. So that is approximately 7 times 10 to the negative 21 joules. But that's the energy of a molecule, right? So that's not a ton of energy, but you figure just the massive number of molecules that you have in there. And then for velocity, well, I can convert the velocity of this into our other kinetic energy equation, EK, where we can say EK is equal to 1/2 times mass in kilograms times velocity squared. So let's do that. I have my EK already. 7 times 10 to the negative 21 is equal to 1/2. Now the mass, what I'm looking for is the mass of a single molecule of nitrogen gas. And so if I know that a molecule of nitrogen gas is 28 divided by 1,000, that would be times 0.028 kilograms. Well, actually that's not quite right, is it? That's the mass for, and then we'll have to divide that by 6.022 times 10 to the 23rd, okay? And then we're gonna solve for the velocity squared. So let's see what we get here. I think this is going to come out all right. 7e to the 21 negative times 2 divided by 0.028 divided by Avogadro's number. And then we'll square root that, and it comes out to equal about 548 meters per second, which is, reasonable. That's about how fast the average gas molecule is moving around the room. Okay, all right, and I think that should get you through most of the basic math for this unit. A few things you'll have to kind of know, like conceptual things. If a gas is not ideal, we can assume that EK, what can we assume about EK or kinetic energy is different than if the gas was ideal? Well, a real gas doesn't have elastic collisions. That's the main thing. In an ideal gas, the molecules never lose energy, but in a real gas, obviously they do. So that's probably what I'm looking for there. So, all right, in the next video, I'm going to show you sort of a more complicated problem, but it's really just we're going to use all of the information that we have been given, only mix it into one problem.